Hi, BC Calc. We're back to our total distance notes. Sorry, we had an internet outage there, so I guess this video will be in two parts. And if I'm being honest, I don't know when the last video cut out. So going back to this page of the notes where we were talking about at the top that when the rate is constant, distance equals rate times time can help us figure out distance traveled. Same idea of thinking of position as equaling velocity times time. But if the velocity is changing over an interval, then we know that this is going to break down into an application of a definite integral. So if we want to find the total distance traveled from A to B, we're going to first start assuming that we have our condition where the velocity is positive. And that makes life a little bit easier anyway. This way, when I find and break this interval up into n subintervals, and then thinking about that the distance traveled would be the velocity at time t sub 1 times the delta t there. If we break it up into small enough intervals and then take the limit as n goes to infinity, we're going to get the total distance traveled. So total distance can be expressed as the definite integral from A to B of v of t dt. Now, again, keeping in mind, this is the case when v of t is greater than or equal to 0. We'll, of course, discuss later on what happens if v of t is negative over the interval at any given moment. Okay, so let's take a look at v of t equals t cubed plus 3t squared. There's our velocity function. The particle's moving along a straight line. What is the distance traveled between t equals 1 and t equals 4? So to find that definite integral and confirm that that is the distance traveled, we have to ask ourselves, is v of t positive on the interval from 1 to 4? So we can confirm that pretty quickly by saying, all right, well, let's maybe set this equal to 0, figure out when the velocity is 0. And that winds up happening if I take out a GCF of t squared, we get t plus 3. So we're going to wind up getting that the velocity is 0 at time equals 0 and then time equals negative 3. Well, yeah, it doesn't really make sense to talk about time equaling negative 3 here. But if I think about what's happening beyond 0, if I plug in, let's say, 1 or 2 or 3 or 4, somewhere on this interval from 1 to 4, what will happen is that this quantity is always positive after t equals 0, no matter what I plug in. So because of that, we can think of this as the definite integral from 1 to 4 of t cubed plus 3t squared dt. That's a pretty easy definite integral for us to find. So this would be t to the 4th over 4 plus, that's actually just t cubed if we use anti-power rule. Upper bound of 4, lower bound of 1. Plugging those in, the total distance traveled is 126.75 units in that straight line. Okay, so if you know something about your velocity function, that it is always positive on the interval, it's a pretty easy application. We're finding the definite integral from 1 to 4 of your velocity function. But suppose that the velocity does change sign on the interval from A to B. What would the integral from A to B give us? If we change sign on the interval from A to B, this integral gives the net change in distance. And that net change in distance is what I think you'll know as the common term for displacement. Okay, so it's kind of where you would wind up if you go to the right a little bit, come back to the left a little bit. It's going to tell you where you would find where your final position would be relative to where you started. Okay, so for example, if I gave you that we travel 7 miles to the east and 2 miles to the west at this stopping place right here, your displacement is 5 miles there, right? If I go 7 miles east and then 2 miles back to the west, relative to our starting position right here, our displacement is 5 miles, but the total distance traveled is 9 miles. We think about how far we physically walk to the right and then back to the left. So if we want total distance, if that's our end goal, we have to think of this in a different instance here. If we want to integrate and find the total distance traveled from, let's say, A to D, we can think of it integrating A to D of the absolute value of your velocity function. That will ensure that we get total distance. Or what we'll also see, probably a little bit more commonly because it's easier for us to do this by hand, is that when we have positive areas, we'll keep the bounds from A to B, and then as soon as I have a negative velocity, we know that this would return negative accumulated area here, so then we have to negate this integral to make it into some positive for our total distance here. So if we want displacement, it's pretty easy, just A to D, and we're fine. But if we're looking for total distance, we have to account for where the velocity is positive versus where the velocity is negative. And if we've got negative velocity, we have to negate that integral then. So let's say if we can take a look at what that would look like in our last example here. And again, for quick comparison purposes, I was just kind of mentioning this anyway, that it's kind of a good comparison to think about total area versus the accumulation, which would have positive and negative areas combined. Distance traveled is going to be a total area versus displacement, which would be adding the positive and negative parts together to figure out your relative position to where you started. So here's an example where it's a little bit different because you're given the position function to start. So if a particle moves along the x-axis, so its position at any time t is given by this equation, x of t, which is also defined here as s of t, find its total distance traveled between t equals 0 and t equals 4. If we happen to know that this position function was, let's say that the velocity was always positive valued, then I could just find x of 4 or s of 4 minus x sub 0. Right, take the initial starting place, take the place where I am after 4 seconds, and subtract those. But in the end, I know that if the velocity is not always positive over that interval, that that's just the displacement. So if I ask for displacement, that would actually just be a pretty quick and easy substitution there. But we have to determine, is the velocity ever negative, meaning we're going in the opposite direction then, over that interval from 0 to 4. So to find v of t, we can quickly apply the power rule here. It's going to be 6t squared minus 18t plus 12. If we go ahead and set that equal to 0, we can divide out the 6 here to make it t squared minus 3t plus 2 equals 0. So we get t minus 1 and t minus 2. So the velocity is 0 at t equals 1 and t equals 2. So in the context of finding the total distance from 0 to 4, let's partition on this interval also around 1 and 2 and see how the velocity is changing here. If we're positive, if we're negative, around these points where the velocity is 0. So from 0 to 1, if you pick 0.5, that's going to be negative, negative for a positive region altogether. And then we stop, and then in this case, if we plug in 1.5, it's positive, negative. So now we're going to turn around and head in the other direction. So yeah, this is not going to be as easy as just plugging in 0 and 4 to the position function. That's definitely going to be a displacement and not a total distance. Finally, if you plug in between 2 and 4, t equals 3 would return positive times positive. So the way you would set up the definite integral in the end is, remember, we're integrating velocity. Integrating velocity would get you back to position here. So because we're positive over the initial interval, we can say it's the integral from 0 to 1 of v of t dt. Okay, our function 6t squared minus 18t plus 12. And then because we're negative from 1 to 2, we're going to subtract that integral from 1 to 2 of v of t dt. And finally, in the last region, add on the rest of the area from 2 to 4 of v of t dt. And in the end, this is something that we could calculate by hand pretty easily, given that this is our velocity function. But to save some time, as I typically do here, I'll tell you that the total distance is 34 units. Okay. There is another way to approach this. This will be most likely the common way that you'll see this, because oftentimes, especially in the homework in the textbook, you'll see that you're given the velocity function. So given the velocity function, figure out where it's positive and negative over the interval, set up the corresponding integral so that we get total distance if that's what we're looking for, and then we kind of go from there. But if we do happen to know the position function, we could actually make a little bit of a table at the bottom and figure out the total distance from there as well. So in the table, we're going to have t and x of t, or s of t. And we're going to put the start point and the end point, and then the two places where the velocity was 0, which were at t equals 1 second and t equals 2 seconds. And we know that the initial position when time is 0 is -4. If you go back to the position function. If you plug in t equals 1, you wind up getting that the position is 1. So the total distance that we've traveled here is a distance of 5 units. Then remember, because we're going negative, we're going to go backwards for a little bit. So how far backwards do we go? Well, if I plug in 2 for the function x of t, you get 0. So this is a total distance here of 1. And finally, if you plug in 4, because it's all positive from t equals 2 to t equals 4, t equals 4, you get 28 here. So from 0 to 28, that's another 28 units total. So therefore, in total, we get 5 plus 1, which is 6, and then 6 plus the 28 is a total of 34 units. Okay. Notice how the displacement here would have been 28 minus the negative 4 would have been 32. So pretty close to the total distance, but certainly not exactly matching here because of that short time and that short distance that we go backwards. So make sure that we're keeping in mind that these would be two valid approaches to this process, but I would say probably more commonly, you'll see it approached from the velocity given. So if we figure out where the velocity is positive and negative over a given interval, then we can set up our definite integral from there. All right, that's part 2 of this lesson. Sorry, we had our tech issues that required this to be split into 2 videos. Let me know if you have any questions next time I see you. Have a good day.